All right, welcome everyone. Today, we're jumping into something that sounds like it's straight out of a sci-fi movie. We're talking about the quantum cheat code.
But first, let me ask you something. What if there was information out there that was physically impossible to copy? Not because our tech isn't good enough, but because the actual laws of physics say, nope, can't do that. This isn't some hypothetical, by the way. This is the reality of the quantum world.
And that entire reality? Well, it's built on one single golden rule, an unbreakable law that kind of sets the stage for everything else we're going to talk about.
That law is the no-cloning theorem. It's basically a cornerstone of quantum mechanics, and it says you cannot make a perfect identical copy of an unknown quantum state. And yeah, that key word there is unknown, and it's a rule that is the complete opposite of how information works for us every single day.
I mean, the difference here is just stark, right? Classical bits, the ones and zeros running your computer right now, you can copy them a billion times and the original is totally fine. But a quantum bit, a qubit, whoa, it's incredibly fragile. Just the act of looking at it, of measuring it, can completely wreck its state. And like we just said, you can't make a backup copy first. No way.
Okay, so here's the really crucial fine print. The theorem isn't saying you can't create a specific quantum state. Not at all. If you know exactly what you want to build, like say a qubit that's a perfect zero, you can make as many as you want. The problem, the impossibility, comes in when someone hands you a qubit in some complex, unknown state and you want to duplicate it without messing it up. That is the line physics just will not let us cross.
But when you tell scientists there's a hard limit, what do? They see it as a challenge. So the story of quantum information isn't just about the rules themselves, it's about the unbelievably clever ways we figured out how to work with them to kind of bend reality's rules.
So this brings up a huge problem. I mean, think about it. If you can't copy a qubit's information, how on earth do you move it? You can't just read the data and send it over the internet because reading it destroys it. So what do you do?
And the answer is quantum teleportation. Now hold on, we're not talking about Star Trek here, beaming people across the galaxy. This is all about moving information. Think of it like this. You're not moving the particle itself, you're just teleporting its quantum state, its essence, if you will. The original particle stays put, its exact quantum identity is just transferred to another particle somewhere else.
Okay, so here's a super simplified look at how this works. You've got our two famous characters, Alice and Bob. First, they need to share a pair of entangled particles ahead of time. You can think of these as two coins that are magically linked, no matter how far apart they are. Now, Alice takes her entangled particle and the unknown qubit she wants to send, and she does this special measurement on both of them together. This gives her two regular old bits of information, which he can just send to Bob in an email, a text message, whatever. Bob gets those two bits, and he uses them as instructions to perform a very specific operation on his particle. And bam, his particle instantly transforms into a perfect replica of the one Alice started with.
And here's the brilliant part, the part that ties it all together. During Alice's measurement, that original qubit state was completely destroyed. So you see, you don't end up with two copies. You end up with one, just in a new place. The information moved, but it was never ever cloned. It perfectly respects that golden rule of the universe. Okay, so that's moving quantum states. But let's stick with communication for a minute. What about sending regular, classical information? How much data do you think you can cram onto a single particle? I mean, the obvious answer seems like it should be one bit, right? A 0 or a 1. But quantum mechanics has another little surprise in store for us. The answer, and this is pretty wild, is 2. You can use a single qubit to reliably send 2 classical bits of information. That is literally double the capacity you'd expect, which is why this next trick is so perfectly named.
It's called super dense coding, and just like with teleportation, what's the secret ingredient? You guessed it, a pre-shared pair of entangled particles. Alice can perform one of 4 specific actions on her particle, which instantly changes Bob's. So by sending just her one particle to Bob, he can then measure them both together and figure out which of the 4 things she did. That lets her send 2 bits of information, 00, 01, 10, or 11. It is another fantastic quantum cheat code.
Now, these weird rules don't just mess with how we communicate. Their real power, the game-changing stuff, really comes to life when we stop just sending information and start actually processing it.
Because all these things we've been calling limitations, like, not being able to copy a state or that weirdness of superposition, they're not bugs, they're features. They are the very things that give quantum computers their unbelievable power. We're talking about calculations that are just flat out impossible for even the fastest supercomputers on the planet.
So let's start with a simple one. Deutsch's problem. Imagine you've got a black box, a function. You put a bit in, you get a bit out. Your job is to figure out if this function is constant, meaning it always spits out the same thing, or balanced, meaning it gives you a 0 for one input and a 1 for the other. Classically, you have to check both inputs. You have to ask 2 questions. But a quantum computer, it can figure it out with just 1 query. Now, it's a small speed up, sure, but it was the very first proof that quantum computers could actually do something better.
And this really gets to the philosophy behind it all, which David Deutsch, the father of quantum computing, put so perfectly. He said that computers are physical objects, and what they can or can't compute is determined by the laws of physics. It's not about being a clever programmer, it's about using the fundamental rules of reality itself. And by using quantum physics, we get access to a whole new type of computation. Okay, so let's scale that up, way up. Imagine you're trying to find a hidden password, an n-bit string of ones and zeros. Classically, to figure it out, you'd basically have to ask n questions to find each bit, one by one. But what if you could find the entire password in just one guess?
Well, the Bernstein-Vazirani algorithm does exactly that. It's incredible. Because of that quantum magic called superposition, which lets a qubit explore a whole bunch of possibilities at the same time, a quantum computer can query that password function just once and determine the entire hidden string in a single operation. This is where you see the quantum advantage is not just a little better, it's a whole different league.
So what does all this mean? We've got these unbreakable laws, but we've also got these incredible workarounds and shortcuts. And this isn't just some fun thought experiment. This is literally the blueprint for a whole new era of technology.
All right, let's wrap this all up. So, what's the quantum rulebook? Rule number 1, you can't copy unknown quantum information. Period. Rule number 2, we can use entanglement as this amazing resource to bend the rules, letting us do things like teleportation and super dense coding. And rule number 3, quantum superposition lets us check a ton of possibilities all at once. And the result of all that? We can solve certain, very important problems exponentially faster than we ever could before.
And that leaves us with this final, absolutely thrilling question. If these quantum computers can crack problems that are basically impossible for our best supercomputers, what are they going to discover about our universe? When we finally turn them loose on the biggest challenges in medicine, in material science, in fundamental physics, what new secrets are they going to unlock? Thanks so much for joining me.